Inductance is often said to be the property of a device or material that resists a change in current and is therefore capable of producing reactance. But what do we mean by resisting a change in current, and how does that even occur, and then how does that produce reactance? So let's look at that in more detail. Inductance is the property of a conductor by which a change in current in the conductor creates a voltage in the conductor itself and in nearby conductors. This induced voltage in turn induces a current that flows in a direction opposite to the original current. The basic conductive device is a coil of wire that we often call an inductor or a solenoid. So let's kind of step through what we just said again, but a little more slowly. So we apply a voltage to a loop of wire. Some sort of voltage gets applied across the terminals of this loop of wire. What that causes is a DC, this is a DC voltage, let's say. A DC voltage will cause a coil to, or a current to flow through that wire. And what we know results is that a magnetic field gets produced around this loop of wire. So you see these little magnetic field vectors that we've drawn. The direction of the magnetic field can be visualized if you take your right hand, you point the thumb in the direction of the current flow. So the current's flowing from here to here. So just point the thumb in the direction of the current flow. And you curl your fingers in the hand of your right hand. And those curled fingers indicate the direction of the magnetic field. So we get these little loops. So current's flowing here. We see the direction of the magnetic field's coming out of the board at the top and into the board. So it's leaving here, it's coming in here. It's looping. It's a little hard once you get here, easier over here. So the direction of the magnetic field vectors are all determined by what we call the right-hand rule. You point your thumb in the direction of current flow. A coil of wire, as we show down here, is going to amplify the effects of a single loop just by stacking a bunch of loops on top of each other, and therefore all these little magnetic field vectors are going to add together because the loops are right next to one another. The net effect of these magnetic field vectors is to add together, pointing along the central axis of the coil. So what happens is I get a net magnetic field vector. It points along the central axis of this coil. So despite the fact that I've got all these little individually rotating magnetic fields, the net effect is a magnetic field that points along the central axis. Now imagine we did this with an AC signal placed on the wire instead of a DC signal. An AC signal placed on the coil will cause the magnetic field to change direction with the AC waveform. So the net effect is that at one peak, the magnetic field is going to point in one direction, and throughout the AC cycle that magnetic field vector is going to rotate until the zero crossing and then rotate back. And it's going to rotate and then rotate back, right? So what happens therefore is the magnetic field is going to change direction with the AC waveform. It's going to point in one direction at the peak of the positive half cycle. It's going to rotate to point into the opposite direction during the change to the negative half cycle. So we see that we get this, what we call an alternating magnetic field. Here a second physical effect is actually going to come into place, or is going to occur. A changing magnetic field, a time-variant magnetic field, in the vicinity of a conducting wire will induce an electric current to flow in the wire. So if I run an AC signal through this, it creates a flipping magnetic field. If I were to put a conductor just parallel to it, a current's going to flow in this conductor. This induced current that gets induced in a conductor near the magnetic field is going to be proportional to the rate at which the magnetic field flips. So if the magnetic field's flipping slowly, the induced current is going to be small. If the magnetic field's flipping quickly, the induced current is going to be large. And the direction of the induced current is in the opposite direction to the current that originally was responsible for producing the magnetic field. So since the coil itself is a conductor, what ends up happening is this flipping magnetic field induces a coil or a current back into the same coil, but the induced current points in the opposite direction or runs in the opposite direction. So I've got one current flowing, from left to right around the coil, and that establishes the alternating magnetic field, but then I get a little tinier current that flows from right to left that opposes the original current. This results in an inductor having an inhibiting effect on the change in current flows. This inhibiting effect will result in a delay or a phase shift of the alternating current with respect to the alternating voltage. So the current will be delayed with respect to the voltage. And what we say is, in an ideal inductor, assuming that this inductive device has no other properties other than inductance, the current will lag behind the voltage by 1/4 cycle, or 90 degrees, right? Quarter cycle, or pi over 2 radians. So we can also visualize this as a 90-degree rotation counterclockwise between the current and the voltage vectors. As the magnetic field increases and decreases during the AC cycle, it is storing and releasing energy. This energy isn't being dissipated, it's really just being exchanged between the magnetic field inside the coil and the rest of the circuit. Because the induced current in an inductor is related to the change in the AC cycle per unit time, the frequency of the AC cycle is very important. Again, the higher the frequency, the faster that magnetic field is changing, and therefore the greater the induced impeding current. The lower the frequency, the lower the effect, and the easier to pass current. We could think of this as a DC current corresponding to the extreme case of zero frequency, and therefore when a DC voltage is applied to an inductor, it will behave like an ordinary piece of wire after a brief charging. One last thing I'd like to point out is that we look at this current voltage graph. We see that the voltage here and current have a relationship where they are 90 degrees out of phase, or a quarter cycle out of phase. So we would see that the current, which is this waveform here with the solid squares, it peaks 90 degrees after the voltage peaks. The passive electrical component that implements inductance as a circuit element is called the inductor, and is depicted using this circuit, this kind of squiggly circuit element here, where L denotes the value of inductor and is measured in henries. L is inductance, and is measured in units of henries. The relationship between the change in current that we just saw and the induced voltage is defined by a quantity called inductance, L, and we would say the voltage across the inductor, VAB, the relationship to that, to the current through it, VAB, is equal to the value of the inductor, L, times the rate of change of the current, di of t dt. Here, di dt represents the time derivative. That's the time derivative of the current, which tells us how fast current is changing its value, or the rate of change of current with respect to time. In context of this definition, what we say is the inductance of 1 Henry would be defined as the amount of inductance required to induce 1 volt when the current is changing at the rate of 1 amp per second. So we would say 1 volt equals 1 Henry at a rate of 1 amp per 1 second, which tells us that Henries are volt seconds per amp. So here we see that the Henry is a derived unit. Going back to V equals L di dt, I'll just write that again. V equals L di dt. From V equals L di dt, the voltage across an inductor will be a maximum when the rate of change of current is the greatest at the zero crossing. So what we see here is we've got 2 sinusoidal graphs. I is the current flowing through an inductor. if we were thinking of this in terms of forcing a sinusoidal current through an inductor, what will result is, if we force that current through the inductor, we'll get a resultant voltage across its terminals. So let's look at this. We say, okay, we've got a current. It's changing. And what we're interested in is the rate of change of the current. We know that when a sinusoidal quantity reaches its peak, its rate of change is 0. Remember, we can visualize the rate of change as a tangent line. That's what a derivative, another way to think of a derivative is a line tangent to the curve, or the slope of the curve at a specific point. So the slope of the curve at its maximum is 0. So the slope at the peak current value is 0. From V equals L di dt, if di dt is 0, voltage has to be 0. So we see this, that the voltage is 0 volts. We then follow the voltage waveform. From calculus, you'll recall that the maximum rate of change of a sinusoidal function occurs at its 0 crossing. That here we have it 0, so we've got the maximum slope right there. You'll also notice that the current is decreasing. Therefore, that's a negative slope. It's a negative rate of change. The values of the current are getting smaller, so we get a negative large number for di dt. Multiply that by L. That's going to give us the largest negative voltage when we go from positive to negative across that 0 crossing. We get a large negative voltage. We then continue on with the current. The current's going to continue to decrease, but the rate of change is decreasing. The di dt is getting smaller until it reaches its max negative value. At that value, we get a di dt again equal to 0, right? So we then multiply di dt of 0 times L. That gives us a voltage of 0. At that point, current is going to start increasing. It's going to cross from being a negative value to a positive value with the AC current waveform. At that point, we get a max positive slope of that sinusoidal quantity. Max positive number times L is going to give us the max voltage right here. So what we see from this is induced voltage reaches its max value a quarter cycle before the current does, or voltage leads the current by 90 degrees in an inductive circuit. Often this is remembered using the mnemonic ELI, where the letters stand for voltage, current, voltage, inductor, and current. So it's voltage, inductor, current. And the order is important. What this means is voltage leads current in an inductor. In this context, inductance can be taken to mean the ratio of the voltage drop produced across a coil to the rate of change of the current that causes the voltage drop. This is really similar to Ohm's law for the resistor, but it turns out that the inductance equation involves the rate of change of current instead of the current itself. It's also casually said that an inductor resists a change of current through its terminals. From this graph here, we see that voltage is at a maximum across the inductor when the rate of change of the current is at its maximum, and the voltage is at 0 when the slope of the current is 0, kind of reinforcing that concept. Although we used a coil of wire to represent the concept of inductance, the same properties can be exhibited by devices that are not coil-shaped. For example, transmission and distribution lines in the power system have inductive properties that must be carefully considered when performing system analysis and design. The overall impeding effect of inductance on a circuit is going to be expressed by its inductive reactance, X sub L. So the general variable used to represent reactance is X. The subscript L tells us that this reactance is the result of an inductive property. This is measured in ohms. Inductive reactance is measured in ohms. And it's the product of the angular frequency and the inductance. So we say X sub L is the product of angular frequency, omega, times the inductance of the device, omega L. This can also be written in terms of the ordinary frequency as 2 pi f L. 2 pi f just being the conversion from angular frequency to ordinary frequency. What we'll notice is that unlike resistance, the reactance is not solely determined by its intrinsic characteristics device. Right? The resistance of a resistor is only dependent on the material properties. Reactance of an inductor is not only dependent on the inductance value, which is a material property, it's also dependent on the frequency of the AC waveform. At high frequency, the greater the induced voltage and impeding current, and therefore the greater the impeding effect At DC current, current is constant and the rate of change is 0, meaning that no induced voltage is created and no impeding current is created. An inductor therefore appears as a short circuit to DC. This property of inductors to represent a high resistance to high frequency will block high frequency signals, and to pass DC is often exploited in electronics when inductors are used as low pass filters. Not a common application in the power system, but in electronics we often call an inductor a low pass filter. That's because of its reactance. Its reactance is smaller at low frequencies. In the power system, inductive reactance is most often found in motor-based loads and transmission and distribution lines.